Hello everyone and welcome again to another lecture. In the last lecture we actually studied about the gradients, and as just a quick recap, we drew a small neural network that was we had one neuron and we had this x and 1, so this was theta naught here, that was theta 1 here, and this was y, which was nothing but theta naught times 1 plus theta 1 times x, which is simply theta naught plus theta 1x. And then I explained as in how we can find this update values for this theta naught using the gradients. So theta naught we can update as in theta naught minus some step size or some value, as in how much proportion of the gradient I will take, right? And then so we calculate some loss functions on it. So we calculate some loss with respect to the actual minus this value, let's say y cap. So and then we actually calculate the loss function with respect to theta naught and we update theta naught. Similarly we can do that for theta 1, something like this. Now or in let me do some more arrangements. So here we have just two parameters, theta naught and theta 1. We can create a theta vector which has both theta naught and theta 1, and then we can simply write this update rule as theta minus eta times del L over del theta. So where you can imagine that this del L over del theta is something like del L over del theta naught, del L over del theta 1, since we have just two parameters. And if you just put theta here and this value here, it will actually become equivalent to this part. So this was something that we already saw last time. Now the question is that first of all, in reality there might be more than two parameters, and in reality we have millions and billions of parameters when we talk about very complex neural network architectures. And then how come we can actually do this efficiently? So do we have to like find out the loss with respect to every parameter separately, independently, and then apply this rule? Well, that would be very complex, right? So that's why gradient is at our core, as in how do we do the update rule. But we now learn another technique that is called as backpropagation, which is the fundamental rule of how neural network does this efficiently. So we are now talking about that backpropagation, or in simple terms BP. It's nothing but it allows neural networks to efficiently compute the gradient. So efficiently computing the gradient, efficient gradient computation. How does it do that? We will actually try to do this using an example. Okay, so let's just take the previous example where we have the function as theta naught plus theta 1 x. So we had this neuron and we have this 1 here and we have this x here. So we have theta naught theta 1, and then we calculate the value y is equals to theta naught plus theta 1 x. So that's how it does, right? And we calculate some loss functions on top of it, and loss comes out to be some value. Let's say this loss is some value k or a constant k. Yeah. Let me just rewrite this so again we know that the output would be simply this here, and we calculate some loss value, and let's say this loss is L. So in other terms, when we compute this computation here, at the output we get the correct output and then we calculate the loss. Loss is what important is. Why? Because using the loss we will calculate the gradient. So how do we do that? Let's just bear with me. What is our objective? Our objective is to calculate del L over del theta naught, del L over del theta 1. Right, here we have y is equals to theta naught plus theta 1x, and this is its neural network. Now let's create this function in a graph form. So we have theta naught plus theta 1x. How does this graph look like? It will look something like this. So if we have theta naught here, if we have theta 1 here, and if we have x here, so theta 1 and x are getting multiplied together, right? So they are getting multiplied together, and then whatever the output we get, we are actually adding it with theta naught, and then we actually get the output, right? So, and using that output we calculate the loss. So just I am representing with L as the loss. Now okay, so in order to compute the gradient with respect to theta naught and theta 1, we will use the chain rule. Now what is chain rule? Let's understand this by an example. What would be del L over del L? That means if I differentiate the loss function with respect to the loss function, well, I will actually get 1. Now you might be wondering, why am I doing differentiation? You'll understand it in a while. So now del L over del L, and that would be 1. So let's consider this as q. That means q, and that means what is q? Q is nothing but theta 1 times x. And then what would be L? L is nothing but q plus theta naught, right? So these are like some intermediary computations that I'm doing here, some intermediate computation. Okay, now let's also imagine that we have some value. Let's say theta naught has the value, let's say 2, and theta 1, let's say 1, and x, let's say 2. Yeah, so we have del L over del L. Now what we are going to do in backpropagation, we have two passes. One is called as the forward pass, and the second is what called as backward pass. So in forward pass, what we do is that we simply go through the computation. So theta naught is 2 here, so theta naught is 2 here, theta 1 is 1 here, and x is 2 here. So now 1 into 2, so the value of q would be 2. So now 2 plus 2, the value of L would be 4. So in this is forward pass. In forward pass, you simply compute the function as stated. As the neurons does that function, you simply compute. Now we take the backward pass, and in backward pass we actually take the loss. We actually take the loss and we propagate it backwards through the network step by step. And at each layer we compute how much of this loss is contributed by every edge or by every layer. Yeah. So in simple terms, we compute how much that layer contributed to the final loss using the chain rule. Let's do this by an example. So del L over del L would be simply 1, right? Now we backpropagate this loss. Okay, so this is 1. Now here if you see, this is my local computation, right? Our objective is to calculate del L over del theta 1. So if somehow I know what is my del L over del q, and if I multiply this by del q over del theta 1, then this would be del L over del theta 1, because you can just imagine that this del q and del q got cancelled out. So this is what called as chain rule. And if you see this very clearly, so this del q over del theta 1 is this part, right? So this is local gradient, and this is del L over del q is actually, so L is here and we are coming towards this part. So this means we are actually propagating this loss backward. So this is actually global, and this is just from here, like this is q and we are going towards theta 1. So this is local. So what is del q over del theta 1? Well, I know that q is equals to theta 1 times x. So del q over del theta 1 would be simply x, right? And what is del L over del Q? Well, I know that L is equals to Q plus theta naught. So del L over del Q would be simply 1. So del L over del theta 1 would be simply x, and the value of x is 2. So now we got del L over del theta 1. So I think you got the idea that what we are doing, we are actually computing the loss globally and we are taking it backwards. And if we want to calculate the loss, if we want to calculate the gradient with respect to a parameter, all we have to do is to simply multiply the local gradient with the oncoming global gradient, and then you can actually get the gradient with respect to that parameter. Similarly, theta naught, what would be the del L over del theta naught? Well, del L over del theta naught is quite simple, as we know that L is equals to Q plus theta naught, so del L over del theta naught would be simply 1. So now we have del L over del theta 1, we have del L over del theta naught, and now we can simply apply this gradient update rule to actually get the new set of parameters. And then after getting new set of parameters, we again update the parameters and again calculate the forward loss, calculate the loss again, do the forward pass, calculate the loss, and then again take it backwards, and then we again update the parameters. We keep on doing so until we get a loss that is much lower. Or there is also something called as epochs that represents the number of times that we have to do. Suppose epochs is 300, that means I need to do this 300 number of times. Yeah, so that's how backpropagation works. Let's also solve another problem, and quite little bit complicated than that. So right up till now we just saw a neural network with just 2 parameters. What if my neural network was something like, so theta naught plus theta 1 x1 plus theta 2 x2. Now we have it's a 3-dimensional regression, and we know that in order to calculate the regression, we also apply softmax function or sigmoid function in the end. And let's say we are also applying sigmoid function, so sigma of this entire thing. So what would be the neural network? Well, if you calculate the neural network, it would be simply 1 x1 x2, right? So we have this neuron in here, and then so this would be theta naught, this would be theta 1, this would be theta 2, and then we get the y, that would be simply theta naught plus theta 1 x1 plus theta 2 x2, and then on top of it we actually apply the sigmoid function. How do I write this? Let's just say sigmoid here, or softmax, or whatever. Right now we are just getting sigmoid here, and then we get some output, and using that output we calculate the loss, and then using that loss we do the backpropagation. But now let's understand how do we do the backpropagation in this part with the same approach. But before doing that, let's first of all again study what is sigmoid. So sigma of x, if you remember in my previous lectures, it was represented something like this. Before going forward, let's first of all understand what is the gradient of the sigma x. That means if I make a small change in x, how does my sigma x change? If I calculate the gradient, how do I do that? Well, if I differentiate it, if you know what is the differentiation of 1 upon x, it's nothing but negative of 1 upon x square times del x over del x, right? Where del x over del x is nothing but 1 in this case. So here in this case, how would it look like? So it would be negative of 1 upon 1 plus e to the power negative x whole square times the differentiation del over del x of 1 plus e to the power negative x. So this would be negative 1 upon e to the power negative x whole square. Now this would be differentiation of 1 is 0, and this would be e to the power negative x times negative 1, right? So this would be e to the power negative x divided by 1 plus e to the power negative x square. Now this I can write something like this. I know that this is quite complicated, but I'm actually giving you a proper understanding of as in how neural network does these computations in the backend. So you have a pretty good understanding of it. So now I can write this something like this, if minus 1 upon 1 plus e to the power negative x whole square, right? I just divided it, like separated it out. So this is got cancelled. So now it is 1 upon 1 plus e to the power negative x minus 1 upon 1 plus e to the power negative x whole square. Now this is nothing but sigma x again. So it is sigma x, and what is this? It is nothing but sigma x whole square, right? If I take sigma x common, then the gradient of sigma is nothing but sigma x times 1 minus sigma x. That's it. Now why I did this differentiation? Because it will make our life much more easier. So now let's do backpropagation one step so that you understand how backpropagation works. So we have y is equals to theta naught plus theta 1 x1 plus theta 2 x2. So if I, yes, one more thing that I didn't mention, the graph that you created here at this part, this is called as computation graph, and this is the graph which your framework makes in the back end, and this computation graph is what it really helped to calculate the gradient, to actually do the backpropagation. So this is what called as computation graph, where you do the forward pass and then calculate the values, you calculate the loss, and then you calculate the gradient of that loss, and then you propagate it backwards to find out the gradient of every parameter, right? So now let's create the computation graph for this. How will that look like? Well, let's see. So we have theta naught here, theta 1 here, theta x1 here, theta 2 here, x2 here. Okay, so we have some multiplication here, we have some multiplication here, and then we add these values in here. So we add them up. Alright, after adding them up, then what? Then we actually take this value and simply add this up here. It's much more complicated than previous part, and there is also a sigma here. So we apply a sigma on top of it, right? And then we calculate our loss. Now let's do the backpropagation again. So okay, before doing backpropagation, let's first of all, because initially at the very first epoch, you will have this theta naught, theta 1, theta 2 randomly assigned. Let's say it is 2, let's say it is 1, and let's say it is also 1, to make our life much more easier. So x1, let's say it is 1, x2, let's say it is 2. Now let's do first of all the forward pass. So forward pass is nothing but simply taking the value and doing the computation. So it is theta naught is 2, theta 1 is 1, x1 is 1, theta 2 is 1, x2 is 2. So 1 into 1 would be 1, 1 into 2 would be 2, 1 plus 2 is 3, 3 plus 2 is 5, and then we calculate the sigma of 5, and then we calculate the loss, right? Yeah, so that's what the forward pass is. Okay, with that in mind, now let's do, first of all, what is sigma of 5? Well, you can like 1 upon 1 plus e to the power negative 5. Well, if you do this, this turns out 993 something something. So if it's very close to 1, so let's just imagine that it is 1, round up to 1, yeah, so that we don't waste time much in here. Okay, after we did that, let's first of all now do the job of gradient. Now let's do del L over del L. Again, del L over del L is 1. Okay, now let's first of all assign some small value. So this is P, let's say this is P, this is let's say R, this is let's say M, this is let's say what, A, and this is let's say B, right? We know that B is equals to sigma of A, or let's you know what, I don't even have to do this B, this is actually L. So L, because L is at the last point, so we can simply take this as L. L is equals to sigma of A. So we now first of all compute, so we have this is the global loss. Now we move backwards. So now we turn out here. So I need to find out what is del L over del A at this point. Well, I know that L is equal to sigma of A. Del L over del A is simply differentiating with respect to A, which we have already done before. This is nothing but sigma of A times 1 minus sigma of A. And that sigma of A is nothing but 1 minus 1 minus 1, that's 0. Now that would make our life quite complicated. Why? You will understand. But let's say this is 0. I mean, okay. Now we have this, what is A? So A is nothing but our theta naught plus M. So A is nothing but theta naught plus M. Now what is del L over del theta naught? The same idea. See, del L over del theta naught is whatever you get the gradient here, that means you follow. So A is equals to theta naught plus M. So first of all you find what is del A over del theta naught. So del A over del theta naught. Okay, now because this is local gradient at this, because this is A plus theta naught, right? So this is actually at this point, this is local gradient, and the oncoming gradient is del L over del A. So if I write del L over del A, now it's like A and A got cancelled, so it is del L over del theta naught. Del A over del theta naught, it's simply 1 because it's just A theta naught times that, what is 1 times del L over del A is already 0. So the gradient of del L over del theta naught would be 0. So I guess now you understand how I'm actually back propagating the loss, like I was here and then I back propagated at this part. Now we can also move down. So A is equals to theta plus naught plus M, right? So what is del A over del M? Local gradient. So right now here earlier we calculated if for this node, this theta naught. Now this time let's calculate towards downwards, that is M. So our local gradient del A over del M would again be 1. Now what would be our del L over del M? Del L over del M would be local gradient times the global gradient that was coming from forward, like from here. So again I'm just doing the same thing, local times global. So earlier I did for upper edge and I got theta naught. Now I'm going for lower edge. Why am I going for lower edge? I cannot directly compute from here to this part because this is way forward, way backwards. I need to go step by step. I'll go from first to M and then from M to R and M to P, and when I got P then I can go to theta naught and theta 1, right? So again del A over del M is 1, del L over del A is 0, so the gradient is 0. Now similarly I got del L over del M. Now what is M? M is R plus P. So M is R plus P. Calculate the local gradient. Del M over del R is 1. Del M over del P is again 1. Now you can simply calculate. Okay, we were here. So now we can simply calculate P. P is equals to theta 2 times X. So P is equals to theta 2 times X. So now del P over del del L over del P would be del M over del P times del L over del M. So it's nothing but here. So we calculate the local gradient and we multiply by the global gradient. So del M over del P we got it as 1, del L over del M we got it from here, that is 0. So hence 0. Similarly del L over del R would be the local gradient del M over del R times del L over del M, which is again 1 times 0, 0. Now we are at this point. Now again the same logic. What is P? P is nothing but theta 2 times x. So calculate the local gradient, that is del P over del theta 2, and then you simply multiply with the oncoming gradient, that is the global gradient. So again the same logic. P is equals to, what is P? Theta 2 times x, theta 2 times x. So local gradient del P over del theta 2 would be x. What's the value of x? X was 1. Was it x1 or x2? This is x2, sorry. So x2, this was I guess 2, right? Yes, it's 2, x1 is 1. So now we have the local gradient. Now you can calculate the global gradient. That means you already have the global gradient. So del L over del theta 2 would be del L over del P times del P over del theta 2. That would be, so this, like, chain rule. So del L over del P was 0 times 2. This is again 0. And similarly you can also calculate this for theta 1. The same logic, that is del L over del theta 1 would be del L over del R times del R over del theta 1, right? What is del L over del R? Del L over del R is 0, and what is R? R is nothing but the same logic, theta 1 times x, and del R over del theta 1 is x1, so this would be again 0 times x1, hence 0. That means the gradient in this case towards every value is 0. Now this is a very interesting case. Now if you see here, the gradient of every parameter is 0. So when I will do theta is equals to theta minus eta times del L over del theta, this is actually 0, hence your theta will not get updated. And when this problem happens, it's called as vanishing gradient, where we don't have the enough gradient value to update our parameters. And why did this happen? If you see here, this actually happened because our sigma, this, like I said, when your x is way too high, it will give you a very constant value towards 1, and then when we differentiated it, it actually became 0, right? So how can you and now you can know that if my gradient is 0, my parameters won't get updated, and if my parameters won't get updated, then I'm just stuck at one place, right? I'm not learning anything. When we say that the neural networks are learning, it actually means that my theta nodes, my parameters are changing in a way that my loss is getting lower. That is what called as the neural networks is learning. And if my parameters don't move, that means my neural network is not learning. That means my loss is not going down and I'm at bad situation. And this can be changed in a various different way. Like instead of sigma parameter sigmoid, you can use some other activation function, right? So this problem is called as the vanishing gradient, and we might talk about this later in the future. Okay, so I guess for today this is it. It was quite mathematical heavy, but my intention was to get a clear picture for you that how backpropagation actually works in practice, and it's very important. Now you know almost now you actually got a pretty good idea how neural network actually works in the background, how parameters, what parameters are, what is the gradient, how these update happens. Now in the next lecture, we will just start with coding everything, because up till now it was more or less more mathematics, but I guess it was very helpful, because this theory was very important for you to know, to actually know how neural network actually works. See you in my next video. Please like it, subscribe my channel. Until next time, Radhe Radhe.